All right, this is quiz 1 for physics 151. Which of these best describes a law? It's an idea that is successful in describing one set of experimental data. All right, that's not true. A description of a physical system is considered to be absolutely true and unchanging. All right, that is the answer. That describes a law. But let's look at some of these others. Something that's been shown to be true over several years. Okay, not a law. That could be called a theory, but not a law. And an analogy that describes how a system works. That could be called a model, but it's definitely not a law. All right. Which of these is not a reason that a standard of measurement is appropriate? Remember, there are 3 reasons. It has to be accurate, it has to be accessible, and it has to be unchanging. All right, so unchanging, accessible, and accurate, those are reasons, so those aren't the answers. But it doesn't have to be simple necessarily. And in fact, most of the standards aren't that simple. So the answer is B. Which of these best describes a model? An idea that's been tested many times, a physical analogy for a system, absolutely true and unchanging principle, or none of these? All right, we've already talked about this in problem number 1, so the answer is B. Which of these numbers is equivalent to this in scientific notation? I'm going to move that decimal place over 3 spaces, so it's going to be 0.00801. Which is option B. Which of these is the standard of measurement for the unit length? The distance across a cesium atom? Okay, no. The frequency of a cesium atom is the standard for time. The diameter of a particular silicon ball? No. That is the future standard for the kilogram, the mass of a particular silicon ball. The length of a bar in France? That used to be the standard for length, but it's not anymore. And the distance that light travels in a particular amount of time. That is the answer, C. Irene is 2 meters tall. A building is 10 meters tall. How tall is the building in Irene? So to do this mathematically, you'd say 10 meters times our conversion factor. 1 Irene is equal to 2 meters. So that's equal to 5 Irenes. So the answer is D. If you want to look at it too, you know, this is our building. That's our building. Here's Irene. She's 2 meters tall, so you need 5 Irenes to go up the height of the building. Okay, how many liters are in 0.05 milliliters? Do this however you like, but I'll do it this way. 0.05 milliliters. In 1 liter, there are 1,000 milliliters. All right, so 0.05 divided by 1,000 is 0.00005. So I should have 4 zeros and a 5. That's A. Ryan is traveling 35 miles per hour. How fast is this in meters per second? So 35 miles per hour. I know that in 1 hour there are 3,600 seconds. And in 1 mile there are 1,600 meters. So 1 mile, 1,600 meters. Do this, 35 divided by 3,600. And then times 1,600. I get 15 or 16 meters per second. So that answer is A for number 8. Lucas travels 24 meters during the time of 48 seconds. What is his average speed? It's just distance over time, my change in my position over my change in time. That's going to be 24 over 48, which is equal to 0.5. 1/2 or 0.5 meters per second. That's D for number 9. Amy can run the 400 meter with a speed of 8 meters per second. How long does it take her to complete the 400 meter? Well, again, V is D over T with a constant speed. And I want to know what is the time. So I'm going to solve this. I'm going to cross multiply, and I'll get VT equals D. And then I'll divide both sides by V. So T then is equal to D divided by V. That's 400 meters over 8 meters per second. 400 divided by 8 is 50 seconds. 50 seconds is A. All right, I can also look at my units here. If I have meters over meters per second. This is the same as meters times seconds over meters, and that cancels out, leaving us with seconds. Consider this distance versus time graph. Which statement best describes the velocity? All right, the slope of this graph gives the velocity. The slope here is small and positive, and then it gradually gets bigger. So the velocity is increasing, A. Miko starts at rest and runs with an acceleration of 2 meters per second squared. What is her velocity after 5 seconds? All right, my velocity is equal to my initial velocity plus my acceleration times time. Starts at rest, so that means that this is 0. So my velocity is just the acceleration, which is 2 meters per second squared, times my time that she runs, that's 5 seconds. So it's 10 meters per second. So C is number 12. You drop a ball and it requires 0.5 seconds to reach the ground. How high is the ball when you release it? So you drop a ball, it starts going down, it reaches the ground. It falls with an acceleration equal to 10 meters per second squared. All right. My time required to reach the ground is 0.5 seconds, and I want to know what is the, let's see, I think we used S here. What is S equal to? What is the height, the distance from here to here? All right, so I know that S is equal to V initial times T plus 1/2 the acceleration time squared. The initial speed, if you drop it, that means you're not throwing it down. So my initial speed is 0. So this whole term goes to 0. So that's 0 plus 1/2 of 10 meters per second squared times T, which is 0.5 seconds. But it's squared, so it's 10 times 1/2 squared, which is 2.5 meters. That's D. Number 13 is D. I think that's the end. There's the equation. So remember, I made a change. There was no SI here. Oh, I'm sorry. I made a mistake here on number 13 too. I forgot the 1/2. So let me fix this. It shouldn't be 2.5. It should be 1.3. Just a calculation error. Sorry, I was doing it in my head. So 1.3 meters. 1.3 meters. 1.3 meters. So that would make this A. Okay, but everything is correct. It was just that very last number is incorrect.